Good day, ladies and gentlemen. This is lecture number 6 of Khazar University for Mechanical Engineering Design class. We have been designing the oil mixer for the last class, and today I will start with some questions students of mine had to me today. So one of them is about helical gears and the stresses on the shaft of the helical gear. So helical gears have three fundamental forces like tangential, axial and radial. And all of these forces act on one point. It's not one point, it's a teeth of the gear. However, we will consider it as one point. So this is F tangential, this is F axial, and also there is F going to the center, F radial. So this is F radial going to the center, F tangential, and also this F axial. Axial is coming to us here. So these are the forces. I know there are books which tell you how to design coefficients, stuff like that, but you should use those books. You should use them as a procedure for design. Nevertheless, you should always think out of the box. You should always use your troubleshoot system, use your skills, use your understanding. You should use your way of designing, your way of analyzing the stresses. You should have your own methodology, your own passion, your own way, your own style. So my style is this. I know forces, I'll get moments, I'll get stresses. That's it. I don't need any methodology. I don't need any methodology to prove myself that this gear will work. But of course I do the procedures as well and compare them to my results and see if I get critical numbers or the procedures get critical numbers. If I get critical numbers and procedures do not get critical numbers, then I raise a question: why did they do such a procedure which doesn't consider like safety factor of 2, for instance? So but if my way is like not critical, like if my way is saying it's okay and procedures also saying it's okay, then it's okay. Why would I bother myself? So shaft. Yeah, there's a shaft and each shaft has bearing on its endings. And usually those bearings are ball bearings. I'm a huge fan of ball bearings because they are cost effective. They can handle 0.15 ratio or 15% of axial force. So if radial force is like 6 tons applicable, it's 15%, let's say 6 by 50, so 0.9 tons can be applied in axial. In cylindrical one it's usually not possible, but in ball bearings it's the case, so you can do that. You can have some axial force in cylindrical ball bearings. Yeah. So let's say you put your gear here. This is your gear. It has T's, and of course you have forces. Yeah, it's a side view, cross section. So it's a cross section. There are balls. This is gear. Yeah, you have axial force. You have radial force, and you have tangential force. As you know, tangential force rotates this this shaft, so shaft doesn't get any stresses from tangential force, because yeah, it maybe gets some infinitesimal, but not in my world, not in my engineering, because you apply force, it rotates. The only force there is the friction force, and friction force of bearings is very small. The friction factor of bearing is 0.0002. So anything multiplied by 0.00002 is very small number for me. So tangential force, I don't care about this force. All I care is F radial and F axial. For F axial, the formulas are like this. So F axial generates a moment around this point, so it creates this bending moment, and this bending moment is applied on the shaft. So this F axial tries to rotate this shaft, and by that I can say that this F axial generates forces here. So I'll call them R. So what are these forces, you will ask me. This is counteracting. Oh, sorry, I draw them wrong way. Wait a minute. So these are forces trying to withstand that moment, which means MO. Oh, I should put it B. B, sorry, it's B forces, it's not R, B. So MO equal B by this distance, I'll call it L. L is the shaft length, yeah. I'll put it here. This shaft distance is L, so L by 2. So B by L by 4, so there are 2 of those B's. So this bending here generates force at the end of the bearings, and that force is moment multiplied by 4 divided by L. Yeah, that's the moment, that's the forces that this axial force generates on the bearings. And yeah, this is generated because shaft has counteract this bending. Yeah, so what happens, you pull it here, here you get some stressful situation, so it gets stressed at this point, and also here you get stressful situation. So when you do this, these 2 points start doing this, and here you get this, here you get that, and counteracting forces are B. So I take this, put here, take this. So that's the point. Of course, it's not easy to explain on YouTube things like this. It's much more easier in a class environment. But let's assume you understood it and continue. So apart from it, so you have these forces, and you also have this F radial. This F radial has 2 counteracting forces, FO, another one here, FO. They both counteract counteract for the shaft. So what happens is very simple. I'll keep B here. What happens is very simple. Shaft is exposed to bending moment. So your shaft is like this. It's like this. Yeah, it's getting bended. So this force generates bending, and you have here counteracting forces, and you also have a moment here which is generated by F, which is M0. You should also consider that. And yeah, and this data, yes, this data gives you the basic information. Very simple. So your shaft, your gear, your bearing, another bearing, force. Here you have a force which creates a bending moment, something like this, and here, yeah. So we draw a force diagram. It's something like this. No, so it's not something like this. It is something like this. So even not like that. Again, I made a mistake. Well, making mistakes is normal, but not in exam. So you go like this, and you go like this. So this is negative, let's say 10. This will be positive 20, since there are 2 negative 10s. So the force diagram is something like this, and the moment diagram, I draw it under it. It will be something like, it's 0 at the end, it goes like this, and at the middle, I'm not sure about this. It was a mistake, because this one is for distributed load. Our one will be something much more different than that. It will be this. Here you have this moment which will increase it, and it will go like this to 0. Something like this. Maybe not 0, but the point is we have this moment generated here. Yeah. Here we don't have the force because it's not radial force, it's actual force, and this is for radial forces. This is the moment. So yeah, we have the moment. Of course I didn't explicitly, I'm explaining it implicitly. I am not going to explicit explanation, but I will do it on online class which we talk to each other. So what you have to do is to calculate sigma bending, which is mc over I. I is pd over 4 by 64. So that's the cross section of shaft, its diameter. You calculate I. C, it's either diameter of the shaft or the radius. I do not, it's radius, sorry, it's C is the radius. Moment, you calculate the moment yourself. And yeah, if you need help with moment calculation, that one I can do for you as well. So it's L moment equal L by force divided by 4. So it's L, force is the radial force, and divided by 4 plus the moment generated here. So you plus the moment. So this is my way. I calculate the bending force, the bending stress, the bending stress. I also know there are other stresses like shear stress, so I also get that as well into my point. So sigma shear equals VQ over IT. So the shear for the thin walled membranes, you can use this formula. Of course it's not a traditional way of calculating shear like they used to calculate shear like force by area, but that's obvious that it will not create much stress, so go with this formula calculated by thin walled systems. And yeah, in VQ over IT, take T diameter because it's not hollow structure, but it's filled like it's shaft. Yeah, it's not thin walled structure, so diameter will be good for you. Yeah, you calculated shear, you calculated bending. There are other stresses like tension, like compression, like torsion. Torsion is not happening because it's rotating easily. Torsion will happen only when the bearings will get the total damage to the system, yeah, but not today. So bending, torsion, buckling or not buckling. I don't see here any buckling because there is no force. Yeah, that's pretty much. So if you have any more questions related to this, we will discuss it in our Microsoft Teams class. Surely. What I suggest you to do is to go by standard procedure and also by my procedure, and I'm pretty sure my procedure, what we calculate, will not create any issue. The stresses I have just calculated will be infinitesimal, so your design will be properly working. All I want you is to finish your design as soon as possible because I'm interested in looking to your 2D graphs. Well, I have to finish the CAD class, the oil mixer 2D drawings, Since most of you do not have SolidWorks software, I'm planning to finish it on the whiteboard. So you can take a paper and repeat my steps. And after the end of the pandemic, I will give some SolidWorks tutorial classes where we will do these designs together so we can back up what we didn't do earlier. So 2D. 2D means you need a ruler and you have a technical data where your name, the name of the checker, the part name, the assembly name, everything is given. So before I start that, I would like to inform you that there are some stuff you have to. So there is gas, no, 0001. Gas means General Assembly 1. It has assemblies which we call SPD, SPD 0001. It has SPD 0002. It has SPD 0004. 3. It may have as much assemblies as complex your design is. And these SPDs have parts. So part 0001, part 0002. So there are 3 categories: general assembly, assembly, parts. That's it. Nothing else. That's how you will do your shop drawings. Yeah. So before looking at parts, people will look at your general assembly, then they will look at your assemblies, and after that they will look at the parts. Okay, let's draw the bottom part of this. Okay, I'm gonna put a nice line here. I'm gonna continue it. It has been ages since I did this. I'm gonna finish it here because I will leave some space for myself. Ages, man, ages. I haven't been doing. These softwares have spoiled me. I have been using softwares which automatically do this. Now I have to do it for each design. Yeah, it's a ridiculous thing to do. Okay. So let's say I've designed it myself for you. Let's say I'll do even more. So let's put here material. It's style 3. I'll put here weight. And yeah, its weight is 2.2 tons, so 2,200 kilograms. Surface area, and you will ask me, why do we need surface area? Of course you need it to paint it, because if you don't know how much surface area, you will not know how much paint you need. Let's say it's 60 meters square, I just assume it. Here you write like 3D, 2D, checker, approver. 3D it's me, 2D it's also me, checker, it's also me, approver, also me. You write the names of people who do that, and here are the signatures of those people. So of course you need more boxes, like boxes telling what part it is. I'll add them, it's not a problem. So it's gas 0001. So general assembly 001. So that's your box, that's your design box. So this has to be, these essentials have to be existing in all your shop drawings, because people, before looking at the design, they look at this. What is it? What is its weight? What its material? And they make decisions. You can also add one more box. Shape. So you can write here, it's a rectangular tube, hollow tube, solid bar, sheet plate. Let's say it's cylinder, yeah? What does it give you? What's the purpose of writing the shape? Shape, of course, it's general assembly, you don't write shapes there, but for parts you should. We'll do it later, yeah? So, point is, if they see cylinder, they send to the part. The point is that if it's cylinder, they send it to the department which works with cylinders, which cuts cylinders. If it's sheet metal, they send it to the department which has plasma machines to cut the metal. If it's round bar, they send it to turning machines to make the operation. So you ease the work for for the people working in shop, yeah. So they read it, they understand what they have to do, how they have to do. From shape they even understand they don't have to read it, they have to give it to others to do it. So you reduce the time, you increase the efficiency. So that's very important. So I'm gonna draw the 2D drawing of the oil mixer now. So it's something like this, I guess. And for side view, I will draw cross section directly. So like this. This. Yeah, it's not a good thing to do. Yeah, I have to use rulers. Yeah. Why I need a ruler? Because I have to dimensionalize it. So let's say it's 2 meters height for the cylinder. I divide it by 100. It makes if I divide 2 meters, so 2 meters is 2000 millimeters. I divide it by 100, it will be 20 millimeters. 20 millimeters is small. I want at least 200 millimeters, so I do it like 10, yeah. I divide it by 10 and go like this. So I draw something like this. And I know that its diameter is 2500, so it will be 250 millimeters here. So it will be something like this, 250, and we go up, sorry, 200, yeah. So what I actually did is very simple. I used a ratio, like, you know what I mean. Like, I reduced the size of the oil mixer by 10 times. So if it's 2 meters, it is 20 yeah, it's 20 centimeters now. The 10 times, yeah, it's 10 times reduced. So it's 10. If you increase it 10 times, it will become very big. Yeah, 10 times. Yeah. So let's do it. So now it's, I have to do its bottom part. So to do its bottom part, you will need this guy. I'm not gonna use it. I'm gonna do it like this. But don't repeat my actions, my moves, because it's not a good way. But I don't have the tools. I don't have this for the marker, so I do it like this. Then I have to do legs. I'll do one leg and say the 3 legs, because that way it's much more easy. Leg height was 200 millimeters, so it will be 2 centimeters here. Yeah. Exactly, and 40 millimeters this length. Everything is exactly perfecto. Very excellent job. So I call it assembly 1, leg multiplied by 3. So I called the leg assembly number 1 and I multiplied it by 3, and now I'm gonna continue, and I'm gonna continue with the walls of this thing. So I need to draw some walls. And these walls I do not like this because it's cross section. What is cross section? Cross section is something you cut by half and show. So it's cutted, so I also have to draw some other parts, like the mixer itself. It's here. It has a shaft with diameter of 80 millimeters, so it's 8 millimeters with this thing. So I draw the shaft for you. Yeah, there is a pipe above. With ball bearings. there is a motor unit which rotates this thing. There is a cap here. There is a breathing unit here. So we have a motor, we have bearings, we have shaft, we have breathing unit, we have other stuff. Yeah, I have to be more detailed, so I'm gonna do it more detailed, yeah. Being more detailed is super hard here, yeah. Super hard, so go back to less detailed. Yeah, I'm gonna go in more detail in assemblies, not here. So I'm gonna go into more details in assemblies, but not here. Oh, yeah. We have this as well. So and yeah, it also has some outlet pipe here. And outlet pipe here. So my point is, it's a general assembly. I'm gonna show you what you have to show in general assembly. So assembly 1, you already showed it, it's leg, there are 3 of them. I'm gonna delete this here. So then this I call assembly 2. And for us, assembly 2 is the body of the oil mixer. This here is assembly 3. This is the mixing unit. Also there's a cap, the top part of it, it's assembly 4. So 4 assemblies, and this inlet outlet I'll call assembly 5. And I will include a ladder with it, so there is a ladder to the insidings of it. I will include a ladder as well. Assembly 1, 2, 3, 4, 5, yeah, it's good. So I'm gonna make a box here. Yeah, and I'm gonna make a big one. Big box. Call it big box. Big box. It will have 5 lines, I guess. 1, 2, 3, 4, and 5. Exactly. Fast. So the name of it. Guess what? I already finished it. So number assembly 1, assembly 2, assembly 3, assembly 4, assembly 5. Name assembly 1 leg, assembly 2 body or tank, assembly 3 the blade, or let's call it blade from that Blade movie, yeah? Vampire Hunter. So assembly 4 it's cap, assembly 5 it's another cap of the cap. Weight, legs 60 kilos, body like 1 ton, blades another 800 kilograms. assembly cap like 200 kilograms, and a cap of the cap it's 120 kilograms, something like this. Material, style 3, this one is style 40x, style 3, so blades are style 40x. And the last one, maybe the paint, everything is GAL 5001. GAL 5001 means blue color. Don't blade the blades, don't paint the blades, because it will work with oil, and as you know, oil is not getting rusted. So this is gas 0001. So by looking at it, well, now I'll show you what the production guys face when they see your drawing. So they look at it and they do this. Okay, great job, good. And they look at it. Okay, assembly number 1, leg. Leg will be done in where? Leg will be done in plasma cutting. Plasma cutting, after that it will go welding. Before welding it goes beveling, preparation for the welding, so then welding. So plasma cutting, welding. So there is a line which does it. A plasma cutting machine, beveling machine, welding machine. So they put it there. Assembly 2, body. Body, what does it need? It needs plasma cutting machine, it needs welding, it needs bending, it needs again welding. So this is the other lines. So plasma cutting, welding, bending, welding, so they put it there. So the blade. For blade they need something extra, like CNC machines, plasma cutting CNC machines. So they put it on the plasma cutting CNC machine, then machining, then welding. Again they also use a turning machine for the shaft, so turning, then assembling. So they put these assemblies into different fields, and at the end they bring them to one master point where they assemble them. And they have assembly guys who are ready to take those parts and connect to each other, give you the product which was designed. Yeah, that's all about gas 0001. Now I'm most likely gonna, I don't see any point in showing you assembly, but I'll show you a part, how to make a part. So let's take some part. Assembly is similar to this, how you call it, to gas 001. You have a box with parts and you look at that box, then go for the parts. So yeah, its weight is different, area is different. So part 001, part 0001, and material is also different. My friends, I'm gonna show you a shaft. I know you like shafts, you're mechanical engineers, so shaft will be good for you. Shape is steel bar. Material for shaft is steel 40x. Weight, I'll say it's 200 kilograms. Area 10 meters square maximum. Our shaft is very long one. It's around 3 meters, I guess. And when you divide 3 meters by 10, it's 30 centimeters. But when I divide its length, like diameter, 80 millimeter by 10, it's 8 millimeters. 8 millimeters are not enough to show you all the parts of it. So I'll need at least I'll need at least 12, 16 millimeters. I'll need at least 16 millimeters of diameter to show you the details of this shaft. And 80 millimeters divided by 16 means 5. So it's 1 to 5, yeah? So 3000 divided by 5 makes 60. No, it makes 600 millimeters. Yeah. Wait. This is 160. Sorry, I'm very sorry. It's not 1 to 5. It's actually different than that. It's 2 to 1. Yeah. 2 to 1. What does 2 to 1 mean? It means it's 2 times longer. So if I do it like this, yeah. If I do it like this, wait a minute. 80, 2. If I do it like this, I have to use 6 meters length, and 6 meter length will not fit on this whiteboard, and that's why I will use this. Like, you don't show all the lengths, you just show the... So let's do it now. Put the other side here. 16. I'll give you the lengths. Give you the length of shaft. So my friends, this is L equal 3000 millimeters. So this is the length of the shaft, but as you see I made it shorter for myself. So let's start it. This is the head of the shaft. Has something like this. So head of the shaft is like this because we will put a bearing there, and in order to put a bearing we will give its diameter. So internal diameter of the bearing is 60 millimeters, and we will also give a tolerance for it, and its tolerance will be H7. Big H because it's external diameter, it's not internal, so big H7. So that's the tolerance for the bearing. And apart from the bearing, we also need a ring seat. And you will ask me, what the hell is a ring seat? Great question, actually. I'll show you it here. This is the ring. This is the ring. You open it, you insert it into this groove there, and then that's it. You put your ring there, and it holds the bearing. It doesn't let the bearing go up. As you see bearing here, so this is the bearing, let's say, it cannot go this direction because there is a shaft wall, but it can go up. So for it not to go up, you put a ring here, and this ring is installable and uninstallable. You can put it and take it out whenever you want. So that's the point. That's the ring you need. So rings vary by diameter, vary by application. It can be internal, external. Here it's external ring, so you know that. Yeah, you put that shaft there, and after you go some miles, there is another. Oh, there is. Yeah, there is another bearing here, also looking for a ring. Another bearing, another ring, again 60 H8 H7, sorry, 60 H7 for the bearing. Apart from it, you need to put some guideline for the machining guide, the turning guide. You should put, machine it to, let's say, like 6.3 or 3.2, yeah, 2.5, let's say, yeah, 2.5. 2.5 means the surface roughness, yeah. You need this for the bearings to sit well, so you put 2.5 here, 2.5 here. You need it because of the bearings. Actually, I made a small mistake. It's K6, man, it's not H7, sorry. It's K6. Small K6. It's internal. Because what does K6 mean? K6 means it's plus 10 to plus 30. So if it's 60 millimeters, the machining guide will do it 60.02 millimeter. It will be bigger, and it will hold the inner cylinder of the bearing very tightly. It's interference. It's perfect fit for the bearing. Yeah, perfect fit. Yeah, I put another line here and finish the shaft. At the end of shaft there will be another part. I'll put this, the threaded hole here. It's threaded so you can put your bolt there. So I'll show you dimensions like these dimensions. I have to show this dimension. You have to show all dimensions as if you are gonna machine it. That way you will understand what is missing and what is not. So if a machining guy looks at it, he says, okay, you put a bearing there, but how much should I machine there for your bearing? So you say 26 millimeters is the bearing length. How much should I machine for the ring? 3 millimeters. How much is the distance between the first bearing and the last bearing? Let's say 500 millimeters. How much is this bearing? Again 26 millimeters. This ring again 3 millimeters. How much is the what bolt is it? It's M20. So bolt. How much is the depth of the bolt? It's 400 millimeters. that, this, how much is the diameter of this? It's, let's say, 59 millimeters. How much is the diameter of that? So you have to put all the details for the guys, because if you don't, they will come to you and tell you, what the hell did you do? I don't understand it. What is this? What's that? Why don't you give the whole information? Why are you making me come here? Why are you making that? Why? So after that they will go and tell his friends, their engineer who doesn't know how to do a shop drawing, will make fun of you in the whole factory. So you have to put all the dimensions, and I think that's enough about this, how would I say, oil mixer. I would like to move to weld design. Little bit easier topic. So I think it would be nice for me to design a valve. So yeah. Designing a valve. Let's make America great again. So there are lots of valve types, and today we will talk about gate valves. Gate valves, it's flanges, cast iron. Yeah, it's how you know what gate valve is. You just need to see PN 16, pressure nominal 16. So it can work at 16 bar pressure. Diameter nominal, it should be like something 100, so 100 millimeters. What else about valves? Well, pressure, diameter, material. So GGG, like 20, like gray cast iron, something like that. 20 means 200 yield strength, 40 means 400 megapascal yield strength. This, then yeah, I think that flange types. So type 21 in the body, so flange type, yeah. Also face-to-face dimensions. I think that's enough for now. Yeah. Let me start drawing a body of the flange, so I should use a ruler. So let's say your face-to-face is 300 millimeters. I'll reduce it 10 times. 300 millimeters is actually this. I will not reduce it. It will be 1 to 1. I'm just gonna do it like this for you. That's it. I've been doing so much of these gate valves that I know them by heart. the cross-sectional view of the gate valve, because I forgot to put this. So for that, put it like this and like this. This is cross-sectional view. So it's cast iron, as you see. And how do I know it's round? Great question, huh? Very easy. I put axisymmetric line. This line means it's round. I put another one here, which one shows that the bonnet part is also round. So I think I'll stop here.